By the late 1930s, Germany stood on the threshold of great ambitions. The Luftwaffe, the air arm of the Third Reich, sought to create a powerful strategic aviation force capable of striking far beyond the borders of Europe. The idea took shape in the mind of General Lieutenant Walther Wever, the Luftwaffe's first chief of staff, who saw long-range bombers as the key to achieving air supremacy. His vision was to build an aircraft capable of reaching targets deep within the Soviet Union or attacking Royal Navy bases in Britain. This vision became the foundation of the Ural Bomber program, a project intended to bring these ambitions to life. The Ural Bomber was envisioned as a heavy bomber able to carry a substantial payload over long distances. Wever believed such an aircraft would be decisive in any war against Germany's main potential adversaries, the USSR and the United Kingdom. In 1936, the Ministry of Aviation launched the project, assigning development to several of the country's leading aircraft manufacturers, including Dornier, Junkers, Heinkel, Henschel, and Messerschmitt. The first tangible results were the Dornier Do-19 and the Junkers Ju-90 prototypes. However, both proved disappointing. The Do-19 was too underpowered to carry its intended armament, while the Ju-90, though moderately successful as a transport aircraft, fell short of the requirements for a true strategic bomber. These setbacks revealed that building such a machine was a daunting challenge, even for Germany's advanced aviation industry. Following the failure of the Ural Bomber, Wever adjusted his approach. He proposed a new concept, the long-range medium bomber, designed to combine extended range with less ambitious technical demands. In June 1936, the ministry's technical department issued new requirements. The aircraft had to cover 5,000 kilometers with a 500-kilogram bomb load, feature powerful remotely operated defensive armament, and have a crew consisting of 2 pilots and a gunner. Manufacturers were given freedom in the choice and number of engines, though a catapult-assisted takeoff was suggested to reduce the required runway length. These revised specifications were sent to Blohm and Voss, Heinkel, Henschel, Junkers, and Messerschmitt. Tragedy struck on June 3, 1936, when Walther Wever was killed in an air crash. His death had a profound impact on the future of Germany's strategic aviation. On April 29, 1937, the Ural Bomber program was officially canceled. Yet work on a new bomber did not stop. Ernst Heinkel Flugzeugwerke, led by the renowned designer Ernst Heinkel, had already begun development of a project under the code name 1041. On June 2, 1937, Heinkel received an order to produce a mock-up of the aircraft, which would later be officially designated the He-177. The ministry's technical department remained optimistic, expecting serial production to begin by late 1940 or early 1941, with the first prototype flight scheduled for the summer of 1938. At this stage, the He-177 project was still in its comfort zone. The strategic bomber concept was taking shape in an atmosphere of high hopes at a time when Germany believed firmly in its technological superiority. With experience from aircraft like the He-70 and the He-111, Heinkel was ready to take on the challenge. Yet the project's ambition, combined with political indecision within the Ministry of Aviation, was already sowing the seeds of future difficulties. The He-177 was intended to become a symbol of German engineering mastery, but formidable trials lay ahead. Once the He-177 project was approved, Germany's Ministry of Aviation set exceptionally high requirements for the new bomber, demands that would ultimately shape its fate. The aircraft was to have a range of 6,500 kilometers with a 1,000-kilogram bomb load, reach a maximum speed of 535 km/h, and be strong enough to carry out shallow-angle dive bombing. These specifications went beyond what contemporary aviation technology could reliably deliver, forcing Heinkel's engineers to search for innovative solutions. The program was led by Siegfried Günther, an experienced designer responsible for earlier successes such as the He-70 and He-111. Work began in September 1936, but the process was complicated by the military's constant changes to the requirements. Initially, the He-177 was to be powered by 2 Daimler-Benz DB601E engines. However, the technical department soon concluded that these engines could not deliver the necessary power. In April 1938, during a special conference, it was decided to use the paired DB606 power plant, essentially 2 12-cylinder DB601s mounted side by side and driving a common propeller shaft through a gearbox. This was a compromise. The twin-engine arrangement reduced drag compared to 4 separate nacelles but introduced new technical challenges. An alternative, the paired Jumo 212 from Junkers, was considered, but Heinkel chose the DB606, which had first been tested on the experimental He 119. As the design progressed, the demands continued to grow. The Luftwaffe called for the wing area to be increased to 100 square meters, ammunition capacity to be raised to 6,000 rounds, and for the installation of advanced radio equipment and an improved fuel system. The crew complement expanded from 3 to 4, requiring a complete redesign of the cockpit. One of the most significant innovations was remotely controlled defensive armament, which promised less aerodynamic drag than manned turrets, though the technology was still immature, adding further risk. The requirement for dive bombing capability also forced the abandonment of a conventional 4-engine layout, as such an airframe would not withstand the stresses of recovery from a dive. Meanwhile, political and strategic pressures persisted. The new head of the technical office, Ernst Udet, repeatedly stated that both Hitler and Göring were skeptical about the need for a long-range bomber, believing there would be no war with Britain as long as Neville Chamberlain remained Prime Minister. Luftwaffe Chief of Staff Hans Jeschonek leaned more toward the proven concept of medium twin-engine bombers, which had performed well in the Spanish Civil War. The He 177 survived partly thanks to Kriegsmarine interest in using it as a long-range reconnaissance platform to cooperate with U-boats. Limited funding, however, slowed progress. A shortage of resources meant that even basic structural tests suffered. The wing never underwent full static testing, a decision that would later cause serious issues. Another change in direction was the abandonment of the initial plan to use an evaporative cooling system for the engines. Günther judged it too risky and switched to conventional radiators. But the larger radiators increased drag, which reduced speed and range. To compensate, additional fuel tanks were installed in the wings, increasing the aircraft's weight from 25 to 29 tons and requiring structural reinforcement. Every design step brought new engineering challenges, forcing the team to balance military demands against technical realities. This phase marked the He 177's entry into unfamiliar territory. The bomber that was meant to be a breakthrough in strategic aviation now faced a hard truth. Overly ambitious requirements, unproven technology, and political instability within the Luftwaffe's leadership. Günther and his team had to solve complex engineering problems under pressure from above and with insufficient resources. The He 177 still had the potential to become a cutting-edge aircraft, but even at the start of development, it was clear that the road to success would be a difficult one. The Heinkel He 177 project entered its practical phase on November 19, 1939, when the first prototype, the He 177 V1, took to the skies at Rechlin. The aircraft was flown by test engineer Franke from the E2 evaluation section. The flight lasted only 12 minutes before being cut short by dangerously high temperatures in the DB606 engines. Despite this, Franke reported good handling during takeoff and landing, but noted several issues: engine shaft vibration, stabilizer inefficiency in certain flight regimes, and mild elevator flutter during abrupt control inputs. These were the first warnings of the aircraft's inherent complexity. 11 days later, the second flight tested the retractable landing gear. This revealed new problems: inadequate hydraulic power, altered handling after flap retraction, and poor performance from the air brakes. In December 1939, test flights resumed, but one ended in an emergency landing after an oil pressure drop shut down an engine. The aircraft glided safely back to the airfield, but the crew noted persistent vibration. Soon after, flights were halted when tail damage was discovered, and the final flight of the year ended with a complete electrical failure. It was becoming clear that the He 177 would need extensive redesign work. The prototype's performance fell far short of requirements. With an empty weight of 13,730 kilograms and a maximum takeoff weight of 23,950 kilograms, it achieved only 460 km/h, a full 80 km/h slower than specified. Cruising speed reached just 410 km/h and maximum range was 4,970 kilometers, roughly 25% less than planned. Armament on the V1 was limited to a rear bomb bay, which protruded slightly from the fuselage due to a decision to accommodate larger caliber bombs. The planned three 13mm MG-131 machine guns in dorsal, ventral, and tail positions were not installed. The second prototype, the He-177V2, flew soon after modifications to the V1. Engineers increased the stabilizer area by 20%, partially eliminating the shaft vibration issue. The aircraft was transferred to Rechlin for further testing, but engine overheating persisted. The DB-606 power plants proved so prone to catching fire that the aircraft later earned the nickname the Luftwaffe's Lighter. The third prototype, He-177V3, was intended for engine testing and arrived at Rechlin in February 1940. During a dive test flown by test pilot Rickert, severe flutter developed in the control surfaces, causing the aircraft to break apart in mid-air after just 2 months of trials. The accident prompted tail modifications to the V1, V4, and V5, then under assembly in Rostock, following the example of the V2. The He-177V4 underwent handling trials with another test pilot, Ursinus, at the Heinkel airfield. On June 27, 1940, over the Baltic Sea, the aircraft was lost in a shallow dive when the propeller pitch control failed. Wreckage recovered from the seabed confirmed the cause. The V4's weight had increased with an empty mass of 14,230 kilograms and a takeoff weight of 24,800 kilograms. The fifth prototype, He-177V5, featured revised armament, including three 13mm MG-131s and a single 7.9mm MG-15 mounted in the nose glazing. But misfortune continued. During early flights, brake system failure caused engine detachment. In early 1941, while simulating a low-level attack, both DB-606 engines caught fire, and the aircraft exploded on impact. The He-177's design featured a number of complex innovations that made testing more difficult. Its Fowler flaps, running the full span of the trailing edge, were split into upper and lower sections. The lower section extended with the flap, while the upper section retained aileron function. However, the wing was not originally designed to bear the extra loads from such flaps, requiring additional reinforcement. The landing gear, with dual struts per nacelle, the inner leg retracting into the fuselage and the outer into the wing, also proved troublesome in the thin wing structure. These innovations, though advanced for their time, brought further challenges during the adaptation phase. Each round of testing revealed new weaknesses. Fire-prone engines, flutter, landing gear issues, and electrical failures underscored how far the aircraft still was from operational readiness. Yet the Heinkel team persisted, working to refine the design in hopes of bringing it closer to a standard suitable for mass production. After a series of troubled trials, the Heinkel He-177 moved closer to the stage of serial production. In July 1939, Heinkel received an order for 20 pre-production He-177A0 bombers, expanded in October to 30 aircraft. Ambitious plans called for 800 bombers to be built by 1943, though this target was overly optimistic. Production began in late 1940 at the Rostock factory, where the first 15 A0s were laid down. Additional units were assigned to the Heinkel plant in Oranienburg, with 5 more to be built under license at the Arado facility in Warnemünde. The first pre-production aircraft, He-177A001, flew in November 1941, marking the project's transition from development to tangible reality. The A0s had weights comparable to the V8 prototype, an empty weight of about 17,225 kilograms, and a maximum takeoff weight of 27,935 kilograms. The crew was increased to 5, and the maximum bomb load reached 2,400 kilograms. Defensive armament consisted of a 7.9mm MG-81 machine gun in the nose mount, a 20mm MG-FF cannon in the lower front gondola, a twin MG-81 mount at the gondola's rear, and 13 mirrored MG-131 machine guns in the dorsal turret and tail position. These aircraft featured a redesigned cockpit and tail assembly, direct results of lessons learned from earlier prototype accidents. Signs of progress began to appear. In 1941, Kampfgeschwader 40, KG-40, was selected to convert to the He-177. Its fourth group, IV KG-40, based in Bordeaux, received the experimental He-177 V6 and V11 for military evaluation. This group would later become the experimental He-177 bomber unit, tasked with crew training. Pilots spoke favorably of the aircraft's handling, noting its pleasant flight characteristics. Tests confirmed that the He-177 could handle its maximum takeoff weight and remain airborne for up to 12 hours. On the He-177A-06, even mock dogfights with a captured British Spitfire were conducted successfully, demonstrating the aircraft's potential. Production of the He-177A-1 began at the Arado plant in Warnemünde, before Heinkel's own Oranienburg facility came online. Between March 1942 and June 1943, Arado produced 130 A-1s. Tail sections and empennage for these aircraft were manufactured at a plant in Milich, Poland. The A-1 appeared in several armament configurations. The A-1R1 carried a pair of 7.9mm MG-81s in the gondola's rear. The A-1R2 featured a remotely operated 13mm MG-131. The A-1R4 had an additional dorsal MG-131 turret, and the A-1R3 carried a reduced ammunition supply for the nose-mounted weapon. Plans were also drawn up for an ultra-long-range heavy fighter variant with twin 30mm cannons in the nose, intended to intercept American B-17 and B-24 bombers ferrying across the Atlantic. Structural improvements accompanied these changes in armament. The bomb bay was modified to carry larger caliber bombs requiring internal redesign. The dual-strut landing gear, each strut with its own wheel and retraction system, became more reliable after hydraulic issues were resolved. The Fowler flaps, a major source of trouble in prototypes, were refined, though their complexity remained a weak point. The reinforced tail reduced the risk of flutter, improving flight safety. This phase marked the point when the He-177 began to take on its intended form. Production was in full swing, and pilots recognized the bomber's potential for long-range, heavy-strike missions. Despite the many challenges still ahead, the He-177 was now proving capable of covering vast distances and delivering a substantial payload. The Heinkel team had reached the milestone they had worked toward from the start, the transition from prototype to operational series aircraft. Yet looming ahead were new trials that would prove the success was only partial. Despite progress in production, the Heinkel He-177 remained plagued by serious problems that proved costly in both technical and human terms. The most critical flaw was the fire hazard posed by its DB606 engines. The paired configuration, two 12-cylinder power plants driving a common propeller shaft through a gearbox, created unique challenges. One of the chief causes of accidents was the shared exhaust manifold for both cylinder banks, which overheated dangerously. When throttling back, the fuel pumps often delivered excess fuel, and leaks in fuel and oil lines produced a volatile mixture. The absence of a fireproof bulkhead between the engines and the wing only worsened the danger. Oil tanks, positioned too close to the hot exhausts, would heat to boiling, losing their lubricating properties and causing catastrophic engine failure. Shattered engine components could rupture these oil tanks, triggering fires. One of the most tragic accidents occurred with the He-177A-01 in May 1941 during bomb armament trials. Both engines caught fire on takeoff, and the aircraft crashed. A similar fate befell the He-177A-02 during engine tests. Just weeks into trials, both DB606s ignited, though in this case the crew managed to land the burning aircraft and escape seconds before it exploded. Accident investigations recommended several changes, lengthening the engine mounts by 20 centimeters, installing a fireproof bulkhead, relocating the oil tank to a safer position, and redesigning the exhaust manifold. Of these, only the oil tank relocation was implemented immediately. Lengthened mounts and a revised exhaust system appeared only later, on production He-177A-3s, along with flame dampers for night operations, added at the insistence of aircrews. Another major issue was insufficient wing strength. During tests of the pre-production He-177A-003, the aircraft lost an entire wing panel under load in a turn. The crew bailed out and survived, but a Rechlin report dated October 9, 1942 revealed that actual wing strength was one-third below calculated values. The cause lay in uneven stiffness across structural components, which led to dangerous deformation under stress. This weakness had gone undetected due to the lack of full-scale static testing, a direct result of budget limitations. The Ministry of Aviation brought back engineer Hertel to reinforce the wings and modify the ailerons, but these improvements were not incorporated until 1943. Dive bombing, and still an official requirement, brought its own dangers. During trials of He-177A1 V-15 on only its second flight, air brakes failed at over 700 km/h, and the bomber slammed into the ground. Further testing uncovered yet another issue. At speeds above 500 km/h, the aircraft developed persistent oscillations, the cause of which was never fully determined. This led to speed restrictions that significantly reduced its combat potential. Even shallow dives were risky as the structure could not tolerate high G-forces. Production brought additional challenges. The Arado plant in Warnemünde, responsible for building the He-177A1, faced shortages of components and high-quality propeller materials. Both metal and wooden blades failed to meet standards, slowing deliveries. By June 1943, 130 A1s had been built, but many were used for trials or crew training rather than combat. Of the 35 pre-production He-177A0s, only 3, V7, V8, and A02, were used for training in Ludwigslust, while others were assigned to specialized trials such as bomb site testing at Tarnwitz. This stage marked the steep cost of the program's ambitions. Fires, structural failures, and design shortcomings eroded confidence in the He-177. Speed limits, weak wings, and persistent production problems all underscored that the aircraft was still far from being a dependable combat machine. These setbacks became a harsh lesson for both the designers and the Luftwaffe, forcing them to reconsider how to approach the bomber's further development. The Heinkel He-177 finally entered combat service, though its operational career was marked by compromises and limited success. In 1942, Kampfgeschwader 40, KG-40 began employing the type, primarily in the role of long-range reconnaissance and for supporting U-boat operations. Based in Bordeaux, the unit's 4th Group, IV KG-40, trained on the aircraft before deploying it operationally. Over time, the He-177 also appeared with KG-1 and KG-100, which operated on the Eastern Front and conducted night raids against Britain. The bomber was adapted to carry HS-293 and Fritz-X guided bombs, enabling it to strike distant targets, including ships, marking the type's first real combat employment and demonstrating its potential as a long-range strike platform. For night operations and reconnaissance, the aircraft received special camouflage. KG-1 and KG-100 machines operating over Britain had matte black undersides with dark gray-black upper surfaces. On the Eastern Front, the Hindenburg wing used uniform light blue-gray RLM-65 or RLM-76 paint with dark gray modeling. In KG-40's maritime role, 6 He-177A3s were repainted in RLM-72 and RLM-73, shades similar to standard RLM-70-71, with green upper surfaces and blue-gray sides marked by dark green models. National markings such as the 750 mm swastika on the fin and crosses on the fuselage and wings, either 1500 mm or 900 mm, often deviated from official standards, especially in operational units where dimensions varied. Production He-177A3s incorporated improvements that partially addressed earlier shortcomings. Reinforced wings and fuselage increased structural strength, while lengthened engine mounts and flame dampers on the exhaust manifolds reduced fire risk. The tailplane was fixed at a +2 counters incidence, and the troublesome Fowler flaps were replaced with simpler Flettner flaps, simplifying the wing design. The dual strut landing gear, retracting into both wing and fuselage, became more reliable thanks to upgraded hydraulics. The DB606 paired engine arrangement still powered a 4.5-meter diameter VDM 4-blade propeller via a reduction gear, while the water and ethylene glycol cooling system was redesigned with autonomous sections to improve survivability. Even with these refinements, the He-177 never became a fully effective combat aircraft. Of the 130 A1s completed by June 1943, many were assigned to training or experimental work. In 1942, 20 airframes were based at Brandenburg, 12 at Fassberg, 7 at Lechfeld, 19 at Ludwigslust, and 25 at Lüneburg, while 20 others were undergoing repairs or being evaluated at test centers. 3 were used for long-range reconnaissance flights under Theodore Roevel's command, and 1 served as a DB-610 testbed for the Ju-288 program. In total, over 1,000 He-177s were built, but their combat use remained limited due to persistent technical problems and poor management decisions. The main cause of failure lay in the Luftwaffe's upper leadership. Indecision within the Ministry of Aviation, conflicts between military and political priorities, and chronic underfunding hindered development. Hitler himself, in January 1943, criticized the idea of a dive-bombing four-engine bomber and the complexity of the DB-606 power plants, yet these requirements remained in place due to earlier commitments. In October 1942, General Oberst Hans Jaschonek suggested using the He-177 for night area attacks on the Eastern Front, and in U-boat support, roles far removed from its original conception as a strategic bomber. Ultimately, scarce resources and overly ambitious demands made the program prohibitively expensive, even for industrially advanced Germany. The He-177's legacy is mixed. On one hand, it embodied advanced technologies. Its coupled engines reduced drag, and its remotely controlled gun positions offered better firing arcs. These ideas would influence future aircraft designs. On the other hand, it became a symbol of the collapse of Germany's strategic bombing ambitions. Technical innovation could not overcome organizational mismanagement, inadequate testing, and unrealistic expectations. The aircraft that was meant to be the pride of the Luftwaffe instead stands as an example of how grand ambitions can shatter against harsh reality.